In this problem, they're asking us to find the absolute maximum and the absolute minimum value of this piecewise function. This is now the interesting part. We're essentially doing the same thing as before, finding absolute extrema. But here now, there is a spice. We have a piecewise function. Now, the first thing that we have to do if we're thinking of the extreme value theorem is, again, to check for continuity. We have to make sure that f of x is continuous in the interval starting with 0. So 0 is going to be the left end point, and 3 is going to be the right end point. Because this is a question about continuity, we already talked about continuity quite a bit in previous chapters. I am going to leave that up to you. You're going to go back to the basic definition of continuity and make sure that this definition is fully satisfied. I'm going to make a note over here, though, that the first thing that we need to do in order to have a perfect analysis is to check that f is continuous. F is continuous in the closed interval 0 to 3. And in fact, it is continuous. Continuity checks nicely in that interval. Then, what I want to do now is to find the critical points. Again, I'm trying to use the extreme value theorem. For that, I need critical points. So, because I have two pieces here, I am going to consider the derivative in the first interval and then the derivative in the second interval. So that means that in the first interval, from 0 to 2, right here, within this interval, the derivative, in other words, f of x is going to be equal to 2x minus 1. So then that implies that the derivative of this function is going to be equal to 2. But because it is equal to 2, then this derivative is never equal to 0. Then that means that we don't get any critical points from the first piece of the piecewise function. All right, now let's go on to the other piece. That is going to go from 2 to 3. So actually, what I should do here is to put open because 2 is technically not included in the second piece. So from 2 to 3. So in this case, we know that the function f of x is equal to x squared minus 5x plus 9. Differentiating this function, that will give us 2x minus 5. Now here, I may be able to get critical points. I'm going to go ahead, take 2x minus 5, and set that equal to 0. That means that 2x is equal to 5. Therefore, x is equal to 5 over 2. And then when I check 5 over 2, to see if 5 over 2 is in my interval right here, I notice that 2.5 is precisely between 0 and 3. So then this is a valid critical point. Now I have to figure out if my function is not differentiable somewhere in the interval 0 to 3. Well, it is always differentiable in the first interval. It is always differentiable in the second interval. So if there is a potential danger for this function not to be differentiable, it will happen at 2, that transition point. Notice right here, exactly when the function transitions from a line to a quadratic, to a parabola. That means that if we want to be super careful, we have to go and check whether f is differentiable at 2. And because it is a piecewise function, 2 is the transition point, you're going to go back to the basic definition of a derivative, the limit definition. You cannot apply techniques of differentiability at x equals 2. This is exactly where the transition takes place. So we're going to go back to basics. However, again, I'm going to leave that up to you to check. It's a quick check by using the limit definition, one of the two formulas that expresses that derivative as a limit. So I'm going to make a note over here that you will check whether f prime of x exists. And it turns out, actually, that f prime of x does not exist at x equals 2. It doesn't exist. So then that tells me immediately that 2 is a critical point. All right, so I'm going to go ahead and circle this, x equals 2, because a quick check, 2 is right there in the domain of the function from 0 to 3. So it's a valid critical point. So now we are ready for the extreme value theorem. So the extreme value theorem, EVT. We're going to go ahead now and compute f of 5 over 2. We will compute f of 2, and now f at the end points, f of 0 and f of 3. Using the function, f of 5 over 2 will be equal to 5 over 2 squared minus 5 times 5 over 2 plus 9. If you're wondering why I am doing this, well, 5 over 2 is 2.5. 2.5 is between 2 and 3. That means that we are working with the second piece of the function. So I take the second piece, which is the quadratic, and substitute 5 over 2 in place of x. Now, when I do the calculations, I should get 11 over 4. Then we're going to go ahead and do the same thing with f of 2. When x is equal to 2, we are dealing with the first piece of the function. So then that's going to be 2 times 2 minus 1. That will give us 4 minus 1, which is going to be equal to 3. Now, f of 0. 0 happens to be again in the first part of the function. So then 2 times 0 minus 1 will be equal to 0 minus 1, negative 1. And then we need f of 3. 3 is on the second part of the function, on the quadratic. So then 3 squared minus 5 times 3 plus 9, that will give me nicely 3. So the absolute maximum, now I'm going to go ahead and look for the highest y value. So then the highest y value that I see here is 3, and also here 3 repeats. That happens when x is equal to 2 and when x is equal to 3. So then this is going to be over here the absolute maximum value. I'm going to do the same thing over here. This is going to be the absolute maximum value. It's exactly the same value. And this happens precisely when x is equal to 2. And here, this happens when x is equal to 3. Now I need the absolute minimum. Well, the absolute minimum value happens is negative 1, which takes place when x is equal to 0. So I'm going to say over here, absolute minimum value is negative 1, and that happens precisely when x is equal to 0. So again, two things that I would love for you to do is to make sure that you settle the continuity. That will be a great way to review continuity. And then to settle that or investigate or somehow show, let's say, that f is not differentiable at x equals 2, which again is a wonderful way to review the basic definition of a derivative.